Namaste to everyone. I welcome you all in my YouTube video channel. Today I will deliver lecture on zeros, singularities and poles. Lecture number 10, in which I will solve some problems on singularities. Before solving problems, we have to remember two important statements, which are: number one, limit point of zeros of a function object is an isolated essential singularity. Number two, limit point of sequence of poles of a function object is a non-isolated essential singularity. Now we solve a problem. Find the kind of singularities of the function cot pi z by z minus a whole square at z equal to 0 and z equal to infinity. Solution. Here function of z equal to cot pi z by z minus a whole square. This equal to cos pi z by sin pi z multiply z minus a whole square. For singularity, denominator equal to 0 implies that z minus a whole square multiply sin pi z equal to 0 implies that z minus a whole square equal to 0 or sin pi z equal to 0 when z minus a whole square equal to 0 implies that z equal to a comma a. Therefore, z equal to a is a pole of order 2 when sin pi z equal to 0 implies that pi z equal to n pi, n equal to 0 plus minus 1 plus minus 2 dot implies that z equal to n implies that z equal to 0 plus minus 1 plus minus 2 dot are simple poles, because 1 has come only once. Here a has come twice, so this is a pole of order 2. Similarly, minus 1 has come once, so minus 1 is a simple pole. Similarly, 0 is a simple pole, 2 is a simple pole, minus 2 is a simple pole, and so on. Now, limit n tends to infinity z equal to limit n tends to infinity n equal to infinity. Therefore, limit point of sequence of poles zero plus minus 1 plus minus 2 is infinitive. Therefore, according to our statement 2, z equal to infinitive is a non-isolated essential singular point. Now we solve the next problem. Problem is find the kind of singularities of the following functions: sin z minus cos z at z equal to infinity. Now we solve this. Let function of z equal to sin z minus cos z. Now we find the zero of function of z. For this, function of z equal to 0 implies that sin z minus cos z equal to 0 implies that sin z equal to cos z implies that sin z by cos z equal to 1 implies that tan z equal to 1 implies that z equal to n pi plus pi by 4, n equal to 0 plus minus 1 plus minus 2 and dot 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 dot. Therefore, z equal to, when n equal to 0, this is pi by 4, pi by 4. When n equal to plus minus 1, this is plus minus pi plus pi by 4 plus minus 2 pi plus pi by 4 dot 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 are zeros of the function fz. Now limit n tends to infinity z equal to limit n tends to infinity n pi plus pi by 4. If n equal to infinity, this is infinity plus pi by 4 is infinity. Therefore, limit point of zeros of the function fz equal to infinity. Therefore, according to the statement 1, concept 1, we know that limit point of zeros of function is an isolated essential singularity. Therefore, z equal to infinity is an isolated essential singularity. Now we solve the next problem. Find the kind of singularities of the following function sin 1 by 1 minus z at z equal to 1. Now we solve this. Let function of z equal to sin 1 by 1 minus z. Here we see that for 1 minus z equal to 0, the function fz is not defined, implies that z equal to 1 is a singular point. For 0 of the function If z equal to 0 implies that sine 1 by 1 minus z equal to 0 implies that 1 by 1 minus z equal to n pi, n equal to 0 plus minus 1 plus minus 2 dot 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 implies that 1 minus z equal to 1 by n pi implies that z equal to 1 minus 1 by n pi, n equal to 0 plus minus 1 plus minus 2 dot 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 are zeros of function of z. Now limit n tends to infinity z equal to 1 minus 1 by infinity, this is 0. Therefore limit point of zeros of the function f z equal to 1. So according to the statement 1, that is concept 1, the limit point of zeros of the function be an isolated essential singularity of the function. Therefore z equal to 1 will be the isolated essential singularity of the function fz. Now we solve the next problem. Next problem is find the kind of singularities of the following function: tan 1 by z at z equal to 0. Now we solve this. Let function of z equal to tan 1 by z. It is clear that for z equal to 0, the function is not defined. Therefore z equal to 0 is a singular point of function of z. Not defined means function of z is not analytic. For having singular point, the function is not analytic at the singular point. Now function of z equal to sine 1 by z by cos 1 by z for singular points. Denominator equal to 0 implies that cos 1 by z equal to 0 implies that 1 by z equal to 2n pi plus minus pi by 2, n equal to 0 plus minus 1 plus minus 2 comma dot 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 implies that z equal to 1 by 2n plus minus half pi, n equal to 0 plus minus 1 plus minus 2 comma dot dot dot. Since 1 by 2n plus minus half pi be the sequence of poles of function of z, limit n tends to infinity, z equal to limit n tends to infinity 1 by 2n plus minus half pi, and this will be equal to 0. Therefore, limit point of sequence of poles of function of z equal to 0. We know that the limit point of sequence of pole of a function is non-isolated essential singular point. Therefore, z equal to 0 is a non-isolated essential singular point. Now we solve the next problem. Next problem is find the kind of the singularities of the following function: 1 minus e to the power z by 1 plus e to the power z at z equal to infinity. Now we solve this. Let function of z equal to 1 minus e to the power z by 1 plus e to the power z for singularity of the function denominator equal to 0 implies that 1 plus e to the power z equal to 0 implies that e to the power z equal to minus 1 equal to e to the power 2n plus 1 pi I, n equal to 0 plus minus 1 plus minus 2 comma dot 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 implies that z equal to 2n plus 1 pi I, n equal to 0 plus minus 1 plus minus 2. These are sequence of simple poles of the function of z. Limit n tends to infinity z equal to limit n tends to infinity 2n plus 1 pi I, when n is infinity. This is infinity. Therefore, limit point of sequence of poles of the function fz equal to infinity. From concept 2, statement 2, we know that limit point of sequence of poles is non-isolated essential singular point. Therefore, z equal to infinity is a non-isolated essential singular point. Now we solve the next problem. Problem is find the kind of singularities of the following function cosec 1 by z at z equal to 0. Now we solve this. Let function of z equal to cosec 1 by z. Here for z equal to 0, the function fz is not defined. Therefore, z equal to 0 is a singular point of the function fz. Since fz equal to cosec 1 by z equal to 1 by sine 1 by z for singular point, denominator equal to 0 implies that sine 1 by z equal to 0 implies that 1 by z equal to n pi, n equal to 0 plus minus 1 plus minus 2 dot 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 so on, implies that z equal to 1 by n pi, n equal to 0 plus minus 1 plus minus 2 and so on. These are sequence of simple poles of the function of z. Limit n tends to infinity, z equal to limit n tends to infinity 1 by n pi. If n equal to infinity, then this is 0. Therefore, limit point of sequence of poles of function of z equal to 0. We know from statement 2 or concept 2 that limit point of sequence of poles is a non-isolated essential singular point. Therefore, z equal to 0 is a non-isolated essential singular point. Thanks for watching my video. If you are satisfied with my presentation and contents, then please click on like button and do subscribe my YouTube channel. Thank you.